All right, let's dive into a pretty amazing cosmic detective story. The main character here, our very own star, the sun. And the mystery we're going to unravel is how scientists managed to unlock over a century of its hidden magnetic history. So here's the fundamental problem. Trying to understand the sun's magnetic activity over the long haul isn't just some academic exercise. It's actually critical for predicting what we call space weather. These are the massive solar flares and eruptions that can and do knock out satellites, mess with our power grids, and just generally wreak havoc on all the tech we depend on. To see the future, you have to understand the past. But for the sun, well, a lot of that past has been a total blank. And this is where the plot thickens. See, we've only been able to directly measure the sun's magnetic fields since about 1908. But, and this is the key, we've been taking these really detailed photographs of it, called spectroheliograms, since way back in the 1890s. So for more than 100 years, these photos have just been sitting in archives, basically holding clues that we couldn't fully read, until now. It turns out the biggest clue was hiding in plain sight the entire time. For well over a century, astronomers knew that the super bright patches on the sun, these things called plages, were directly tied to areas with really intense magnetic fields. So the light itself is kind of like a fingerprint for magnetism. But proving that connection with enough precision to actually rebuild history, well, that was the real challenge. This timeline really puts that knowledge gap into perspective, doesn't it? I mean, we have these beautiful early photos from the 1890s, but it took until 1908 for someone to even measure the magnetic field in a single sunspot. And we didn't get regular full-sun magnetic maps until the 1960s. So the big question for scientists was, could they use the super high-res modern data from satellites like the Solar Dynamics Observatory, the SDO, to finally crack the code hidden in those century-old pictures? So to use the old photos, you first have to prove the brightness to magnetism link works perfectly with your best modern data. But of course there was a problem. Even our most sophisticated space telescopes, well, they're not perfect. You could say their eyes get a little tired over time. Okay, take a look at this. This graph shows the raw brightness data coming from the SDO satellite over a few years. See that steady downward slope? It makes it look like the sun is actually getting dimmer, but it's not. That's just an illusion, an artifact caused by the satellite's detectors slowly wearing out after years of getting blasted by radiation in space. So step one was basically a digital cleanup job on this cosmic lens. So how'd they fix it? With this really clever four-step process. First, they used magnetic data to find all the calm or quiet parts of the sun. Then they built a model of what the sun's normal background glow should look like. From that model, they created a digital correction filter. And finally, they applied that filter to every single image, essentially wiping away all the wear and tear from the satellite's camera. And wow, just look at the result. On the left, you've got the raw, uncalibrated image. On the right, the final, cleaned-up version. Suddenly, all those subtle details, the bright and dark features, they just pop right out. Now that they had this totally reliable dataset, the real detective work could finally get started. Okay, so the data is clean. Now the researchers could finally get to the main event. And they did something that sounds kind of crazy. They decided to analyze and sort every single pixel from thousands of images of the sun, just to see if a pattern would emerge linking brightness to magnetism. And the big breakthrough? It came from this graph right here. What you're seeing is the distribution of pixel brightness. That blue line, that's a quiet day on the sun. The orange line, that's a really active day. See the difference? On an active day, you get these long tails at both ends. That means you have way more extremely dark pixels and way more extremely bright ones. This was it. This was the key. So that insight led them to define two very specific categories. They said, okay, any pixel with a brightness contrast below 0.5, we're going to call that dark. That's your sunspots. And any pixel with a contrast above 1.95, we'll call that bright. Those are the active regions, the plages. By setting these simple thresholds, they could turn any picture of the sun into a simplified map of just bright spots, dark spots, and normal spots. And this brings us to the moment of truth. They had this map based purely on how bright the pixels were. The huge question was, would this map of light actually match the real map of the sun's magnetic field? And the answer was an absolutely resounding yes. I mean, look at this. The map on the left was made just by sorting pixels into bright and dark. The one on the right is the actual magnetic map from the exact same day. The resemblance is just stunning. The bright and dark areas, which stand for moderate and intense magnetic fields, they line up almost perfectly. This was the smoking gun. But they didn't just eyeball it, of course. They crunched the numbers. And get this, a staggering 92.4% of all the pixels they flagged as bright were in fact located inside confirmed magnetic regions. This was no fluke. It was an incredibly strong statistical link. They had proved it. Brightness is an excellent proxy for magnetism. Of course, in science, it's almost never a 100% perfect fit. And the small discrepancies here actually tell their own interesting story. As you can see here, the method isn't quite as accurate right around the fuzzy edges of sunspots. And it turns out that's because in those specific spots, the magnetic field is laying much more horizontally, which changes the brightness we see. Understanding these tiny imperfections is actually what makes the whole method so scientifically solid. Okay, so we've walked through this complex process of cleaning the data and proving the link, but what's the big payoff? Why does confirming all this with just a few years of modern data matter so much? It really all boils down to this one powerful conclusion. Because of this research, we now know we can look at a simple photograph of the sun, literally just count the areas that are brighter or darker than average, and from that simple count, we can reliably reconstruct a map of its entire magnetic field. And that is the absolute game changer. This technique is like finding the Rosetta Stone for solar physics. It lets scientists go back into those dusty archives, to all those photos from the 1890s and the early 1900s, and finally read those missing pages of the sun's history. We can now fill in over 100 years of magnetic data that we thought was lost forever. And having this new, much longer history is incredibly useful. It helps scientists get a much better handle on the long-term cycles of solar activity. And that, in turn, lets them build better forecast models for space weather, giving us more of a heads up to protect our satellites and our power grids. It even helps us understand the magnetic behavior of countless other stars out there that are just like our sun. So we'll end on this thought. By blending old-school observations with cutting-edge analytical techniques, scientists unlocked a century of lost data about our own star. It really makes you wonder, doesn't it? Now that this code has been cracked, what other cosmic secrets are just sitting there waiting for us in old photographs of the sky?